Okay, so how is everyone today? Good, I hope. Okay, so let's jump right into it. Last time, just a recap. We talked about solving equations. So solving equations. And what's the phrase? Is it you say let loose a bombshell? Bombshell? Yeah, will say it like this. We let loose a bombshell, and that was that we've solved a lot of equations in this class, and surely you solved a bunch of equations in high school. But last time we realized that, there can be a lot more to it than what we've done previously in this semester and what might have been your previous experience altogether. So in particular, when you are solving interesting equations, that is more or less to say almost any equation except for the simplest possible kind, the very first thing you need to do is calculate the natural domain of the equation. Which is to say, you need to find the set of all inputs such that the equation has any value whatsoever. The kinds of things that you need to avoid, the kinds of things that put a restriction upon the natural domain, are things like divisions by zero and what else? Negative inputs to even radicals. Okay. Then, in step 2, you find solution candidates using algebraic operations on the equation. But remember, we talked about algebraic operations on the equation and the fact that equations have a logical value. Equations, their logical value can be true or false. And some operations always preserve that value, and other operations do not always preserve them. And sometimes you need to use them anyway. So that's interesting. Then after you find solution candidates 3, you exclude candidates that are not in the natural domain, which you found in step 1. So most of the equations that you solved in previous math classes, and most of the equations that we solved before this last week, in this class for that matter, the natural domain was the entire set. Like nothing was excluded. So step 3 never came up. It just never came up, but it's going to come up from now on. And step 4 is that besides exclusions from the natural domain, what else we can exclude for a different matter? What? Right. We'll exclude candidates which don't satisfy the original equation. Because the thing is, in step 2, you're finding solution candidates by performing algebraic operations on equations. You start with the first one. You make an operation, that's a new equation. You do another operation, that's yet another one. If you did 10 different operations, you have 11 different equations. And the solutions satisfy the last one. The question is do they satisfy the first one? Well, under what circumstance might they satisfy the last one but not the first one? I agree with that, but specifically I want to know something about 2. Something about if we have a first equation and then you make an operation, new equation, operation, new equation. Yeah?
You did an operation that changed the logical value.
Right. This comes up when one of the operations from step 2 does not preserve logical value. So we saw an example last time where that occurred. Which operation, so that raises the question, which operations did we specifically mention that do not preserve the logical value of an equation?
Squaring both sides.
Squaring both sides.
Negative
That makes a restriction in the natural domain. So that's an issue for step 1.
absolute value of both sides?
Multiplication by 0. Because remember, they come in pairs, right? Because given an equation, multiplying both sides, if that's the forward direction, multiplying, then the reverse direction is dividing. So you cannot multiply both sides by 0 for the same reason you can't divide by 0. And because squaring and square root are the same thing but in the opposite direction, in a sense, the math word for that is inverse. Because squaring both sides doesn't preserve logical value, neither does square roots, and you have to handle it carefully. Okay, so then the thing that we saw last time more or less boiled down to the following observation. -3 equal 3. So is that, in the first place, is that an equation? Yes. What's its logical value? False. It's false. Suppose we take this equation and we square both sides, remembering that caret means the exponent operator. So then -3 and 3, we're going to square these. Then what is -3 all squared? 9. And then 3 squared is also 9. This is an equation which is true, and the thing that you have to look for is that this is a surprise, right? So we performed an operation, square both sides. The truth was not preserved from false to true. Okay, good. And we did an example of that last time. Any question about this? Okay, so let's have another example of solving equations, and then we'll move on to something even more, to something that has even more moving parts. Okay, so here's a nice hidden block. That is to say, this is like me being back in my office making an exercise. I'm going to take, so can someone give me a smallish positive integer? 4. And I'm going to square that and get 16, and then I'm going to negate it. So you gave me the idea of 4, and I came to that one. Then now I'll just take some other positive smallish prime. How about 7? And I'm going to, from these two numbers, I'm going to do the following. So y plus 16 multiplied by y minus 7. If I multiply this out and collect like terms, then I get y squared plus 9y minus 70 plus 42 is 112. Again, this is just me making an exercise. So here's the exercise. Please solve the following. Please solve w to exponent 4 is equal to 112 minus 9w squared. And we're going to do this in the complex numbers. So again, right, remember the rule is that this part is invisible. You can't see it. And furthermore, I claim that somehow this question that I'm asking you has something to do with that. Okay. So this one's interesting. This equation has, well, the right-hand side is a polynomial in W. What's its degree? 2. It's degree 2. And the right-hand side is also a polynomial in W. What's its degree? 4. So this is an equation of degree 4. This is the first kind. This is the first time we've ever done an equation of degree 4 so far. So let's be really careful and let's compute the natural domain. So please remind me, what are the things that we need to watch out for when we're computing natural domain? Okay. So are there any divisions? There's none. So no division by 0. So that's good, I suppose. What's the other thing we need to watch out for? That's when we're dealing with equations. Right, putting negative values into even radicals. But wait a second. Would that be a problem on this exercise? No, right? Why not? Well, okay, on the one hand, there's no radicals of any kind. But suppose there were. I claim it would still be fine. Why?
It's in the complex numbers.
It's in the complex numbers, right? It's in the complex numbers. So there's no radicals, no even radicals. But even if there were, it would still be okay. Because we're in the complex numbers. As a result, what is the natural domain of this in this exercise? Not all reals. So the answer is not negative infinity to infinity. It's not all reals or anything like that, because what's the answer?
In the complex numbers?
Yeah, the natural domain is the complex numbers, of course, right? Because that's what the question is stated in. So now, complex numbers, and you could think, one way to imagine them is it's sort of like, well, it's a set in which it's okay to put negative inputs into even radicals. That's the kind of thing it is. Does it also overcome division by 0? No, it does not. Right. Right. Now, under no circumstance does I can think of no mathematical circumstance in which somehow division by 0 becomes okay. Not even in the complex numbers. Okay. Good. So 2. Now we're going to find solution candidates. Okay. So the first thing I'm going to do is I'm going to take this equation and I'm going to get all the terms on one side. So getting all the terms on one side, it looks like w to exponent 4 plus 9w to exponent 2 minus 112 is equal to 0. Now, the reason why, in the end, I'm doing that is that the actual fact of the matter is that up until we started talking about these interesting equations, we really only solved two kinds of equations. One of them that we solved was linear equations, things that look like 5 times x plus 3 is equal to 10. Okay, then you just collect like terms, add and divide, multiply. Those are the easiest thing you can imagine. Then the next kind we did was quadratic equations. That's really the only other kind of equation we've solved. Linear ones and quadratic ones. So to a large extent, this region of the class that we're in, from an instructor's point of view, is sort of like, let's play hide the quadratic. Well, somehow I've hidden the quadratic, and this is like a seek and find, right? I claim that, well, in the first place, this isn't a quadratic because quadratic equations have to have degree 2. What's the degree of this one? 4. So this isn't a quadratic, at least not directly. I want to remind you of something that we learned at the beginning of the semester, near the beginning, and that is that and for an expression like this, x to exponent 3 and then raised to exponent 5, we carefully remembered that the exponent means repeated multiplication, and then we went all the way through the repetition and then counted up all the individual x's. If you were to do that, how many x's would there be? There'd be 15 of them. And so, we've got a rule that says that when the exponents look like that, you can multiply them. But the door swings both ways, which is to say that if you were dealing with x to exponent 15, then you could write it like that if that was more convenient for you. You could also write it as x to 5 to 3. That would be just fine also. So what I'm saying is that w to exponent 4 can be written in a manner like that. How can it be written? W squared squared, right? So I'm going to write it like this. W squared squared plus 9 w squared minus 112 equals 0. And here's what I want you to observe, is that in the way that we've written this, w squared occurs in more than one place. So it occurs right there where it's being squared. So suppose I cover that up for a minute. And it also occurs right there where it's being multiplied by 9. So what I want you to see is that I'm covering up w squared. So it is like something squared plus 9 times the same something minus 112 equals 0. So what I'm saying is that let's replace, to make it look easier on our eyes, let's replace w squared with a single variable. So what name do you want to use?
P.
P is the first one that I heard. So I'll say let P be w squared. So what is this equation when you replace w squareds with p's? It is, I agree, but what is it specifically? Very good. P squared plus 9p minus 112 equal to 0. And then, oh, I get it. It was a quadratic, it was hidden. Okay, that's what I meant by more or less in this region that we're in, the majority of these equations are somehow, we're playing the game, let's hide the quadratic. Okay, so here's a quadratic in P. We can solve every conceivable quadratic with the quadratic formula. But that's a little bit, if it's not necessary, it's a little bit heavy-handed. Maybe we could do it the easy way. Can you think of two numbers whose product is negative 112 and whose sum is 9? Maybe 16 and negative 7 would do it, right? Oh yeah, maybe they would. Now, that might seem kind of silly, right? that that we're literally solving an exercise that is up there, but I'm trying to emphasize that this is exactly what I'm doing back in my office. I'm doing exactly that. And that is exactly what all textbook authors are doing also. That's the game. Okay, so now we have the product of two things is equal to 0. So either the first thing is 0 or the second thing is 0. Now, I want to point something out in case you might have missed it. Notice that it's the product of two things equal to 0. What if it was something like the product of two things is equal to 8? Would it be the case that then either the first thing is 8 or the second thing is 8? No, right? Because that might be like 2 and 4 or something, right? No, 0 is special because when you have the product of things equal to 0, it is necessarily true that one of them is 0. Nothing else could conceivably cause that. At least one of them is 0. Okay, so then this one equation splits into two possibilities. The first possibility is that p plus 16 is 0. The second possibility is that p minus 7 is 0. And so this one kind of complicated equation split into two different, really pretty easy equations. Okay, so then that means that it is either the case that p is negative 16 or p is 7. So is this the answer to the exercise? No. Right, because notice that the exercise was phrased in terms of variable w. Currently we're talking about p's, and for that reason this couldn't possibly be the answer. So how do we get back to w's? Right, we've got to remember, oh yeah, we just wrote p because that would look simpler on our eyes, but in fact p is w squared. That's what it actually is. So w squared is negative 16, or w squared is 7. All right, so now we need to continue these possibilities. So now I'm going to cover this one up because it's bothersome for a moment, and I'm going to look at this one because it's the easy one. So I'm covering up the difficulty for a second. What we're asking ourselves is, well, what kind of thing is such that you could square it and get 7? Square root of 7, right? What a terrific name. Square root of 7 would do it. Is there anything else that would? Negative square root of 7, right? So two w's will do this. The square root of 7 and also negative square root of 7. So this one equation splits into 2. So it might be the case that w is negative square root 7, or w is square root 7. Because when you square that, you get 7, and when you square that, you get 7. Any question about just this part? Okay, so now the part that I'm covering up, that I was covering up, so let's have a look at this one. And this one should give you a brief pause. I claim that this one should give you a brief pause. Why?
Because there's a negative as a radical square, which is difficult unless you're in the complex, which we're talking.
Right. So now we're asking ourselves, well, what kind of w could we square and end up with negative 16? Yeah, right. So how about would a positive real w square to be negative 16 if it was positive real? No, no positive real. What about a negative real? Would a negative real square to be negative 16? No. Would 0 do it? No, right? No real whatsoever will do this. So do we throw in the towel for this one? No, right? We're in the complex numbers. I know some of you kind of feel like I'm beating the dead horse there, but I'm just trying to make sure it's clear. So because we're in the complex numbers, yes, it is in fact possible to find things that will square to -16. That's completely possible. So if you hadn't noticed it there, then you would notice it here. You say, okay, well, I'm squaring something, so in fact there should be two possibilities. One of the possibilities is that W is the square root of that thing. Square to the right-hand side. The other possibility is W is negative that. Okay, so if the question in your mind of complex hadn't come up, it should come up now most definitely, because here we have it, literally, a negative value inside of a square root. So is it permissible? It is. So the negative can come out of the radical. It comes out as I, and the 16 can then come out, and 16 comes out as 4. So as a result, the possibilities are, well, negative 4i from the first one, positive 4i from the second one, negative square root 7, and positive square root 7. So we have 4 candidates. 4 different candidates. That's interesting. This is the first time in this class where there's been more than 2 candidates. Okay, so here's 4 of them. Now we need to start making exclusions. So exclusions. So which of them do we need to exclude on account of the natural domain?
I mean, the ones without an I don't quickly appear to be in the complex numbers.
Okay. Well, so would you agree that the square root of 7 is in the first place equal to the square root of 7? So that much? Okay. And then would you also agree that it's equal to the square root of 7 plus 0? Would you agree that it's equal to the square root of 7 plus 0 I? So in fact, every real number is a complex number with imaginary part equal to 0. So square root of 7 is a complex number. Right, they're all fine because the natural domain is all of the complex numbers. So that means that yeah, if you're a complex number, you come on to the party. Okay, so none of them get none of them get excluded on that basis. What is the other reason we might have to exclude? Right. So let me write down. So no exclusions. No exclusions due to natural domain, because the natural domain is all of the complex numbers. Then we need to ask, what about the original equation? Well, please remind me, under what circumstance could it come to pass that we perform a sequence of operations and our candidates satisfy the last equation but not the first one? Mm-hmm. Right. If we performed an operation somewhere that was, one of the iffy ones, one of the ones that could modify the logical value. Did we do any such operations? No, right? Because all the things that we did here, these are all things that occurred before we even talked about logical value. And these are all safe, right? These are like these operations of, factoring, and then the product of two things is 0, and this square root business. those are fundamental tools, but they're also fundamentally safe. You know, they're like the when you have kids play with Play-Doh and you've got the plastic knives. That's what these are. You couldn't possibly injure yourselves with these.
Let me ask you a quick question.
Uh-huh.
We said that squaring both sides of an equation
Mhm.
can be problematic, but I thought we also said that the inverse of that could also potentially be problematic, which would
Yes.
be square root
I
of both sides.
I don't dispute. I agree entirely.
Which I would say, well, we did do that, right?
So we did it. Arguably here and here,
Mhm.
right?
But that's on both sides of the same side of an equation.
What we did is we accounted for all possibilities.
I guess what I was saying is they're both on the right side of the equal sign. I mean, they both come from the 7. You're not really even doing both sides of it.
Well, not exactly, because so as an intermediate here. So this is just an aside. Now, as an intermediate step, we could have written the square root of w squared is equal to the square root of 7, so that we did square root of both sides, right? And then what's the square root of w squared?
So we did do square root of both sides.
Right. So we really did do square root of both sides, but this machinery of taking w squared equal a constant and then splitting it into the two possibilities, that's safe and bulletproof. It can't go wrong. So the answer is that there's not going to be any exclusions. No exclusions because all operations preserve logical value. Now, if you're not really sure, if you're not confident about that, then it is always okay to just plug them in and check. You can just plug them in and remove all doubt. I promise you that they all work. Good. Yes?
So on our WEX, where we were given a problem like this,
Mm-hmm.
and we determined that there were no exclusions because they all satisfied the original equation,
Mm-hmm.
would we have to prove that by plugging all of them into the original equation, or could we just write like an explanation?
You just write just exactly what I did. No exclusions because all operations preserve the logical value. But that's not like a, it's not like a magic phrase, right? If you write it and that's not actually true, then.
We
Yeah.
wouldn't have to plug in all of the values to it.
Right. Right. Good. Any question about this? Other questions? Okay. So now, so solving equations has a bunch of moving parts, right? You've got to carefully watch. Not only do you have to perform these mechanical operations that most people associate with math, like okay, we're adding and all that, but you also have to keep track of other concerns like the natural domain and the logical value of an equation and whether or not that's a legitimate thing to have done in the first place and all that. So there's a lot of moving parts. So because that was so enjoyable, let's move on to something that has even more moving parts. Now we're going to talk about inequalities. So let A, B, and C be in the reals. And A less than B an inequality. So I take it as a given that you understand what I mean when I say that it is a fact that 13 is less than 14. That's true. And it is also a fact that the statement 13 greater than 14 is false. Okay, that much. Understand that this is an inequality, but I'm not making any suggestion about whether or not its logical value is true or false. I'm just saying it's an inequality. So one thing that you're allowed to do is you're always allowed to add both the same thing to both sides. So adding C to both sides of a less than b preserves logical value. So to give you an example of what I mean, 13 less than 14. That's an inequality. What is its logical value?
False.
True, right?
Oh, yeah.
It's true.
Not an equal sign.
Right, it's less than, yeah. Less than. So suppose that we add the same number to both sides. We'll add 8 to both sides. The new left-hand side is 21. The new right-hand side is 22. So 21 less than 22. That's an inequality. What's its logical value? True. And what I want you to observe is, well, we started with true and we ended with true. Okay. Similarly, here's an inequality. 2018 less than 1314. So now, again, we have to kind of squish this uncertainty. Is this an inequality? Yes, it is. Because what an inequality is it's two expressions. One of them we refer to as the left-hand side. The other we refer to as the right-hand side. And then there's this symbol in between them. So is this an inequality? Yes, it is. What is its logical value? It's false. That just means that it's an inequality whose logical value happens to be false. Okay, suppose that we add, I don't know, 50 to both sides. The new left-hand side is 2068. The new right-hand side is 1364. That is also an inequality, and it is also false. And what I want you to observe is that, well, the logical value was preserved. Terrific. It is always permissible to add the same thing to both sides. Yes?
Just out of curiosity, is an inequality considered an equation, or are those two different?
They're different things. They're similar in the sense that they have, you can think of it like two arguments, the left one and the right one. And they also are, when they're defined, their value is always false or true. But equations, both sides have to have the same value to be true, whereas inequalities, you just need them to be ordered correctly. And for those of you who, maybe you haven't seen inequalities in a long time, the way it works, and as it happens, I have a first grader who just recently was going over these. So I'm really fighting myself with myself to not write the following kind of thing, because with her I write it like this. I write 13 and then I write 14 and I write the inequality like this. Right? Because the alligator, right, eats the bigger number. Okay, that's the right way. Okay, the bigger one. Good. So when we were talking about equations, the next thing we talked about was multiplying. So multiplying both sides by c preserves the logical value. And then when we were talking about equations, we had to go on, for this is true for any c. You can never go wrong. It's the safest thing you could possibly do. Add the same thing or subtract the same thing to both sides. Multiplying it when we were dealing with equations, there was one exception. What was the one exception? 0. So this was as long, we still have that exception, as long as c is not 0, and now we've got even a new thing. So I'm going to leave a blank there, and we're going to have to fill that in. So it's still not okay to multiply both sides by 0. That's still not okay. But we need to figure out what else isn't okay, or what needs to go in that blank anyhow. So how about 13 less than 14? Well, that's an inequality whose logical value is true. Suppose we multiply both sides by 2. The new left-hand side is 26. The new right-hand side is 28. And do you observe that that's still true? So I expect there to be no surprise with that. Similarly, 2018 less than 1314, that is an inequality whose logical value is false. Suppose that, so it's false. Suppose we multiply both sides by 2. The new left-hand side is 4036. The new right-hand side is 2628. How about that? False or true? False. So, again, I expect there to be no surprise. Now, I won't even bother writing it down because I hope it to be obvious. What if we were to multiply both sides by 0? This one, say? It doesn't matter which one, but suppose we do this one. The new left-hand side would be, and the new right-hand side, 0. Well, is 0 less than 0? It is not. So multiplying by 0 is, and for that matter, dividing by 0 is just as impermissible as it ever was. Okay. How about this? 13 less than 14. That is an inequality whose logical value is true. Suppose now we multiply by -2. Then, the left-hand side is -26, and the right-hand side is -28. Now, here's an inequality, and my question is what is its logical value? That's false. Right? Because in fact, on the number line, if you like, -28 is further to the left than -26. So that's false. So, whoa. I'm putting double exclamation mark here because I want to make sure that this is surprising. Yes?
So if you were to multiply by a negative number, would you just change
We'll do that in just a second. But yes. So if we took a false inequality like this one, 2018 less than 1314, that's an inequality whose logical value is false. Now suppose we multiply it, that inequality by -2. The new left-hand side is -4036. The new right-hand side is -2628. So how about this inequality? What's its logical value? True. And again, I want you to see. Okay. Well, what I want you to see is that in both cases, what happened is that the logical value flipped. In this case, from true to false. In this case, from false to true. So, where did I put my? There it is. So the logical value flips when you multiply, and understand when I say multiply, I also mean divide by negative. Okay, so now I agree with some of you who are trying to speak up and say, but I agree entirely. When in practice, when you're doing these things, the way that you make it right is that when you're when you're doing something like this, 13 less than 14, that is an inequality that is true. If you want to multiply or divide by a negative number, and if you want it to be the case that the resulting inequality, the resulting logical value is the same as it was before, so it's true now and we want it to be true in the end, then you still carry out the arithmetic. The left-hand side is still negative 26. The right-hand side is still negative 28. But to make it true now, what do? You flip the inequality. So what I want you to see is that now the inequality is preserved, but there's a cost, or something that goes with it. Notice that the direction of the inequality flipped. Okay, so what's the additional rule?
Well, the original rule is that it's, as long as it's not a negative number.
Well, but we want to still be able to do it without, we want to still be able to proceed.
So then, as long, and when it's a negative number, you flip the sign.
Right. So, and you flip the inequality when C is negative. So it's not necessary to do any flipping when C is positive. So in a sense, what I want you to observe is that the case when you're multiplying both sides by C, when C is positive, in a sense, it works just like equations. When C is negative, you can still do it, but you've got to flip the direction of the inequality. Why did that not come up with equations?
Because there's no such thing as switching an equal sign.
Right. It's just as simple as that. Equations don't have a direction. Right? They're not pointing one way or the other. But inequalities do have a direction. They are pointing some way. Okay. Fine. Let's solve one exercise, and then we'll be finished for today. So please solve. How about 2 less than 2 times x minus 10 less or equal 23. So now already I'm introducing something new in the first exercise. Okay, so specifically what I want you to observe is that when we were dealing with equations just had just had two positions, the left position, which we're calling the left-hand side, and the right-hand side. Just two of them. But already here we have three positions. So the meaning of this, this means it's just a short way to write two inequalities that must be true at the same time. 2 less than 2 times x minus 10 and 2 times x minus 10 less or equal 23. It just means those two, which raises the question that, well, if that's all that it means, why do we write it that way? Why don't we just write that? Yeah, because it's less writing, right? The same reason why humans do anything, right? it's just easier. All right, fine. But do understand that there's an inequality with three positions, left, middle, and right. Do understand that that means that in principle I can make an inequality with any number of positions, right? 47 positions, it'd be fine. I would never do that in a real exercise, but understand that it's conceptually fine. So now, but the fact that the inequalities, when you have a string of them with like three positions, they proceed in pairs, right? The first pair, the next pair, the next pair, the next pair. What if we were trying to solve that inequality? What would you do? You'd want to add 10. The first thing you'd want to do is add 10 to both sides, right? You might phrase it like move the 10 over, but that means add 10 to both sides. What if we were solving this inequality? What would you want to do? You'd want to add 10 to both sides. So can you agree that in all circumstances, what you'd want to do is add 10 to both sides? Okay, so what we're going to do is add 10 to all positions. So we'll add 10 to the left, middle, and right positions. The new left position is 12. The new middle position is 2x. The new right position is 33. And again, we have an inequality string that really means this inequality is true and that inequality is true. All right. What if we were solving that? What would we do? We'd want to divide by 2. What if we were solving that? We'd want to divide by 2. So what are we going to do? Divide all positions by 2. And then we'll be right on top of the answer. The new left position is 6. The middle position is x. The right position is, but wait a minute, we just divided. Wait a second. I thought we have to flip the direction when you divide. Ah, yeah. Okay, good. If it had been negative, too, we'd had to flip them around. Okay. So then this one will be 16 and a half. Yeah. So then on such exercises, I'll say, give it to me in algebraic and interval and plot notation. Which one is this?
Algebraic.
Algebraic. How do you write it in interval notation?
6.
Negative infinity.
No.
No, it's got it as no, yeah. So
Close
just 6
bracket
is
6 and square bracket.
Right. Open at 6. Closed at 16 and a half. And then as a plot, open at 6. Closed at 16 and a half. And as fun as this is, we're going to get into the real fun on Wednesday when we deal with nonlinear inequalities. Okay, so have a nice Monday.